Relaxed Knapsack QAOA approach step by step. Finally, we can have a look at what happens with the quantum state of the system in every step of the relaxed Knapsack QAOA algorithm. Let's consider a small example that is shown on a screen. The solution to this problem is 0, 1, so we have to use the wind turbine on the day 1 and the solar cell on the day 2. Since our schedule contains only 2 days, we need 2 qubits to store the decision variable z for these days. These are index qubits. Then we need 4 qubits to store the total cost for each of 4 possible combinations, and 1 qubit as a flag to mark the undesired situations. We consider only the first iteration step for gamma and beta. This is the first application of parameterized unitary operators. First, we apply Hadamard gates to the index qubits. This creates a state at which the probability to measure any of 4 possible combinations for the schedule is the same. Then, we want to encode the total return for every combination into a phase. To do that, we perform simple math and separate a global phase factor, which we can ignore. Since z can be either 0 or 1, the remaining expression means that we should add the difference in returns delta lambda with superscript t to the states when z is equal to 1. This is done by applying a phase gate with the rotation angle delta. After phase return, the probability to measure a certain state is not the same for every state anymore, and is defined by the squared value of the numerical phase factor before the state. During the cost calculation step, we encode the total cost corresponding to each of the possible combinations to the data qubits in a binary form. Then we should mark the states with a total cost larger than Cmax. In this particular example, we have only one such state. It is a combination with indices 1, 1. In the constraint testing phase, we set the flag qubit to 1 for the state with indices 1, 1. In the next step, we want to encode the second part of Hamiltonian, the penalty. In this example, it is quite easy, because we only need to add the phase to state 1, 1, where the flag qubit is equal to 1. We redefine the expression for the penalty via angle theta. At this moment, the Hamiltonian, which represents the function which we want to maximize, is completely encoded into the system. Therefore, we can reset the data and flag qubits, because we need them for the next iterations with other gammas and betas. This happens in reinitialization step. After that, we want to apply a mixing operation. In this step, we simply apply rotation on angle to beta around the x-axis to each index qubit. The action of this operation to states 0 and 1 is shown on the screen. So, this is what happens if we apply the Rx operation to index qubits in our quantum state. Now we can insert this expression into the main formula. After some simple math, we get an expression for the state of the system after the application of the mixer in the first iteration. As you may see, all phases are totally mixed up. The phases, which we just so carefully attached to a certain pattern in indices, are mixed and present in each numerical factor in front of the state. Then we should apply the phase return with the next value of gamma to this state. But we will not do that. Instead, we can watch how each iteration step over gamma and beta change the probability distribution. To solve problem 4C in IBM Quantum Challenge Fall 2021, we don't need to care about the number of steps, which is p, and parameters beta and gamma. They are already optimized for us. As you may see from the histogram, each next iteration increases the probability of the right answer, which is 0, 1. The bit order in the histogram is reversed.